lecture. That will be the last lecture for today, and our last speaker is Romain Paulus from Salesforce. He's calling us from California. It's early morning there, and here it's already evening. But yeah, but we're still going to talk about machine translation. So, are you ready to start showing your slides?
Yes,
to start your lecture.
Can you see my slides right here?
Okay. Yes, we can see them. Okay. So let's begin.
Right. Thank you everyone for attending today, and thank you for the DeepHack organizers for inviting me to give you this lecture today. So I'd like to present to you some recent advancements in the neural machine translation. This will go over some work that has been done both within my research team as well as related work that has been done in other teams too. And I really hope that some of the ideas that I will show you today will be useful for you this week. So before we go into more detail, I'd like to give you a bit more details about the work I do and the work that's done within my team. So I am a lead research scientist at Salesforce Research, which is a fairly new research group that has been in existence for about a year and a half. And we are based in Palo Alto, California. So within my group, we do mostly deep learning-based research around all kinds of NLP problems, as well as computer vision, multitask learning, reinforcement learning, and also optimization in general. And I specifically focus on NLP problems such as state generation, as well as abstractive summarization. And before that, I was a founding engineer of MetaMind, which was a deep learning startup where people could upload their image or text data online, and we will train and serve APIs for classified models with them. And before that, I obtained my master's in computer science and web development from the School of ISEP in Paris. So what's the motivation for this talk today? Machine translation has had very big breakthroughs in the past few years with using deep learning and neural networks, which is something that has not been seen in the field for the past 60 years or so of its existence. From the entire history of the field, we have gone from rule-based systems to statistical machine translation, and now deep learning is mostly the standard way of approaching this problem, except for a few restricted domains where rule-based or statistical-based methods are still used to have best performance. So why are neural networks so performant for machine translation? One of the first things to consider is that we can train them end-to-end. It requires very little pre-processing and very little feature extraction to have a state-of-the-art performance with enough data. That's the second point as well. If we have enough data, deep learning-based systems are basically the best at making use of millions of sentence pairs. And the third part is that we can modify these architectures very easily and make use for new problems that require maybe different kinds of languages or different constraints as well. But the field is far from being solved, and there are still some limitations that prevent us from obtaining human performance with these models. First, it always requires large amounts of labels if we want to obtain good performance, which means that it's not really an issue if we train on very common languages like English or German, for which we have already existing parallel data. But for lower source languages that are either rare or just don't have a big online presence, this is still an issue with neural networks. And moreover, these networks have millions of parameters for the most performant ones, which means that they're still fairly slow to train and fairly slow to use at inference speed. It's not that much of an issue when we have very large hardware, like many GPUs in parallel, but we can still do better. And that's also related to the third problem, which is it's hard to scale these to very long documents, which is why most of the datasets we use today are only considering one or a few sentences every time, and not entire web pages or entire books, for example. If we want to be efficient at translating very long documents, as well as translating documents in a more accurate way, we need to understand the context in which these documents have been created or in which sentences have been spoken. So we humans are very good at incorporating latent context from everything we see around us, but for neural networks, we have to make this explicit for them to know exactly how to change the way they translate things based on external factors. So today we're not going to have time to look into all these limitations, but I want to focus on 3 different aspects that recent work has been able to improve on. So first, I'm going to go into a lot of detail of how we have succeeded in making faster translation models using alternative architecture and different ways of training it. Second, we can make use of different kinds of data and that go outside of the parallel corpora to use multitask, multilingual, and also transfer learning machine translation. And thirdly, to use also more data and to make use of more performant models, we're going to look into recent advancements into semi-supervised as well as first tries in unsupervised machine translation, which is still in its infancy, but I think it's a very exciting development that has been only around for a couple of years. So first, let's see how we can speed up neural networks for machine translation. So if you have attended the tutorial earlier, or if you have been in the field for long enough, you must be familiar with the standard encoder-decoder recurrent network architecture. So here are two main figures showing the main components of this architecture. In the first one, you see the encoder network that takes into an input A, B, and C, and then computes hidden states for this input, and then generates output translation words one at a time, W, X, Y, and Z. One way to make these models even more performant, especially on long sequences, is to use the attention mechanism that will compute the dot product between the input and the output in the decoder at every decoder step, and then create a weighted sum of the context vectors with these weights. So this architecture is based purely on recurrent networks. Here, all the signal blocks are recurrent layers. You can even use bidirectional layers or multiple layers on top of each other, usually using LSTMs or GRUs. So how do we go about speeding things up? Well, we all know that if we want to have a better performance when we have a neural network, all we have to do is to stir the pile of data and linear algebra until we get it right. But to speed things up, it's not that simple. We might stir the pile all we want, but it's still very hard to understand why it's being slow. So instead, we should look into the actual time that's being spent in this network and why we can make things faster. So what if we want to make the model faster? We just have to remove the RNNs. Well, it's not that simple. The RNNs are the basic building blocks of this architecture, which is why they are so performant. But if we remove them, then we are basically back to the bag-of-word models that are being used before the deep learning era. So it's not really useful. The RNNs played a very crucial part into incorporating context between the words. If we only look at the word without context, we have no idea how they play between each other and which ones are related. So we can remove the RNNs to make them faster, but we have to find alternatives to still have a good performance. So if we look around in the literature and ways to read sequences that don't use RNNs, one very obvious answer is to use convolutional networks. So you may have seen these networks mostly used in image processing and image recognition. And the way they work is they use convolutional operations followed by max pooling operations. So here we compare the two RNNs and CNNs. The red parts are linear operations, and the blue blocks are functions that don't use any parameters. So this can be like pooling or gating or addition functions. So as you can see here, each continuous block is a block that can be computed in parallel using GPUs or even CPUs. The issue with LSTMs and all of the recurrent networks in general is that they alternate in the LSTM linear layer operations that cannot be parallelized. You have to run first the linear layer for one item and then for the next one, etc., in a timely fashion. But on the other hand, if we want to use CNNs entirely for the entire text sequence, these CNN features are time invariant. So yes, it will have some combinations between words that are directly under a convolutional operation, but then it will be hard to compute long-term dependencies between other words that are very far from each other. So instead, my colleague James Bradbury has developed a new system that will take the best of both worlds of the LSTM and the CNN that's called the Quasi-Recurrent neural network. So here we have the same kinds of operations that are linear or convolutions in red. And then in blue, we have a pooling operation that actually uses gates that are being computed before, which means that we still keep the linear operation of the LSTM, the first one. And then we're able to do the pooling operation very fast without any parameters and without any matrix multiplications. So how it is done in practice? We can see the operations here. We compute three elements: the Z element, which is the value vector, F and O are gates. And here X is the input sequence, and the star are convolutional operations. So here, just like the CNN, this can be run in parallel for a given sequence. Once we have the Z and the gates F and O, we can compute two hidden states that are very similar to the LSTM. We can compute the memory state C and the output state H. And this is all using element-wise operations between the values and the gates we have. So given the input and output format of this network, it can basically be replaced in any architectures and removing RNNs and removing them to use QRNNs instead. So let's try this. Let's try to use QRNNs for translation. So one little modifications we have to do to make sure that we can use QRNNs into sequence-to-sequence models is to initialize the hidden state of the decoder. So this is usually done by taking the C and H vectors of the encoder at the last layer and then making them equal to the encoder states at the first decoder state. The issue here is that we can see that the states are used in the blue layer in the pooling layer, and they are not used in the computing of the values or gates. So this is not practical if we want the encoder to affect the computation of the decoder. So instead, what we do is we take the last hidden states of the encoder and use them in the linear layer as well, only for a decoder. That way we can affect the computation of the gates and the outputs. And after that, we can stack multiple layers, just like a standard sequence-to-sequence architecture. We use a very similar attention mechanism, but we also add linear and output gates afterwards. So let's see how this does on some experiments. So here we're going to try this on character-level machine translation. This is a more challenging task than word-level machine translation, because for the same text, with character level, you have a longer sequence since you have more characters, which means that a model, whichever you use, whether it's based on LSTMs or QRNNs, has to learn long-term dependencies between characters that can be very distant from each other. Which is why if you look at this table that has been trained on WSLT, the word-level models still do better in terms of blue score. But still, if we compare a sequence-to-sequence model based on the QRNN with one based on the LSTM, we can see that for the same number of layers, which is 4, in both the encoder and decoder, we obtain almost 3 blue scores more than the LSTM with QRNN. And in addition, since all we wanted was to speed things up, it actually does make the network 4 times faster, which is exactly what we wanted. So to go into more detail, we can try to look at exactly what parts of the model are being sped up when we use the QRNN. So here, this is a training time on 20 examples with 105 time steps. And the computation time can be split between 3 different parts. We have the recurrent layers, we have the softmax layer that is used to generate a new word, and we have the optimization overhead, which includes gradient clipping, L2 regularization, and stochastic gradient descent as well. So as expected, the softmax does not change at all because that's not the part that the QRNN replaces, but the recurrent layers are still better than an LSTM that's implemented completely on GPUs as well. And on the right side, you can see the speed up between the QRNN and the LSTM if you use a 320 unit network. So depending on the batch size you use and the sequence length you use, you have different speedups that go between 1.4 times to 16 times faster. So that's something you have to keep in mind when you want to speed up your network as well. Also depends still on sequence length and on the batch size you use. We can also inspect the activation weights of the QRNN and see exactly what kind of things it's paying attention to when it reads a sequence. So here, this is being trained on a sentiment analysis task, which is given a movie review. You have to guess whether the movie review gives a positive or a negative sentiment about the movie in question. So here, if you look at the time step, this is looking from top to bottom at a specific movie review. We're only showing the last part of the review here, which goes like this. Not exactly a bad story, which is the beginning here. And you can see the weights are being really activated. And then in between the word 120 and 160, nothing very relevant happens in the review until it reaches the end, which means I recommend this movie to everyone, even if you never played the game. So here the model paid attention to that last part because it has the word recommend, so it knows it is relevant for the task at hand, which is analyze the sentiment. In summary, this QRNN can be used to replace any RNN, either as an encoder or a decoder with a few modifications. It's clearly faster than LSTM, and the speedup factor depends on the batch size and the sequence length as well. But for the same number of parameters, it gives speedup improvements every time. And it also beats the LSTM for character-level machine translation. But here we've only replaced one part of the model. We can wonder if we can do a bit better by maybe looking at other parts of the model. For example, what if we use even more convolutions? And this is what this model that has been developed by researchers at Facebook is about. Here, this is a completely convolutional sequence-to-sequence architecture. The way to look at this figure, if you start from the top and you have the encoder with the input sequence, they agree, then you run it through a convolution layer, where for as many inputs as you have, you generate as many convolution outputs here. At the bottom left part, you have the previously generated words for the output, and at the bottom right, you have the currently generated ones. So what you notice here is that there is no temporal pooling or gating, unlike the QRNN or the LSTM that we have used, which means that for every input, you have as many outputs as you want. So what do we do if we have no pooling at all? Well, we can stack multiple layers on top of each other, which means that a given convolution at the top layer will be able to look at more words at the same time, which is the same principle of stacked convolutional networks for images too. And here we actually have nonlinearities in other parts. Since we don't have them in the temporal layer, we have them for each unit as the output of a convolution. We have what's called the gated linear unit. It's a simple gating mechanism that uses only one vector to gate itself, basically. You can also notice here we have residual connections, both between the inputs and the outputs as well. So here, if you look at the embeddings, it has a skip connection going to the outputs of the GLU. And if you look at the attention function, it also has a skip connection that completely bypasses the attention and just uses the existing embeddings. And here we only show one layer for the encoder and one for decoder. One thing to keep in mind is that when we have multiple decoder layers, we also have multiple attentions, which is called a multi-step attention. Furthermore, as I've mentioned, there is no temporal pooling in this network. So if we only use word embeddings, we have no way to know which words are coming first and which words are coming last. And we need that kind of information if we want to understand the meaning and the context of a sentence. So instead, the author of these papers are introducing positional embeddings. So these are similar to word vectors, but these ones do not change based on the position, no matter which word and which example they are associated with. That way, the hope is that the model can learn which words coming first or coming after the other ones will affect the context of the whole sentence. And in practice, you have the word embeddings that are trained on glove or in other similar fashion, W, and you have the positional ones, P. And as an input of the convolutions, you use the sum of the two of them, E. And as I mentioned before, we have skip connections in the attention, which is why for this weighted sum, we also include the embeddings here as well. And this is a detail of the gated linear unit that I've mentioned before. Here, y is the output of the convolution layer, and we split y into two vectors, a and b, of equal length. And the way we do nonlinearities is just to do a with an element-wise product of a sigmoid of b. And this ensures that we have a fixed number of nonlinearities, which means that the model is also easier to train and has less vanishing gradients than LSTM. So to try the efficiency of this model, we do some experiments, but unlike the previous ones where we tried character level MT, here we try a word piece vocabulary. So there are different ways of doing a word piece vocabulary. Here the authors use the byte pair encoding one that's very widely used. So the way it works is that you factor existing words of a language into subword units. And it has multiple advantages. If you do this kind of splitting of words between different subtokens, then you have a smaller vocabulary overall than if you used each word at its own token. It has also a better representation if you want to have synthetic or agglutinative languages. which is the case of most languages in this parallel corpora like English or German. And then it also helps to represent rare or unknown words, because every time if you have an unknown word, unless it's a name entity, you can usually decompose it into morphemes and subword tokens that already exist in your vocabulary, which means you have a better representation power of the entire words as well. And so we tried this on 3 language pairs, English to Romanian, English to German, and English to French. And we compared the convolutional sequence-to-sequence against some LSTM-based methods, such as the GRU and the Google NMT model. And in all cases, it has a higher blue score than the previous approaches, which is awesome. And if you look into the English to French, it even outperforms the Google NMT model that uses a fine-tuning step with reinforcement learning to optimize the blue score directly. And here in the convolutional one, you don't need any fine-tuning or any reinforcement learning. So this is very impressive. So the question, is this actually faster than the LSTM? So if we look at the total compute time for one of the dev sets, which is 6,000 sentences, and if we batch them with 120 sentences per batch, then it is between 10 times and 20 times faster than the Google MT paper that's based on LSTMs. And the difference in factors depends mostly on which hardware you're using. But whether you use CPUs or different kinds of GPUs, there is still at least a 10x speedup. And as I've mentioned 2 slides ago, we have what's called a multi-step attention, which means that for each decoder layer, we compute different attention layers, which means that we can see different kinds of interactions between the input and output sentence depending on which level you're looking at. So in some layers, you can see the layer 1, it learns some alignments that are very standard to what you expect from an attention function to do. But then in some other layers, it pays attention to more specific words, maybe trying to see how some words influence the whole context of the sentence and how some words interact with each other as well. So in summary, this is a practical and fast architecture that uses many components, mainly convolutions, but also gated linear units, multi-step attention, and skip connections. And it does better than LSTM-based methods, such as the Google NMT architecture on many language pairs using a WordPress vocabulary. And it has the expected very impressive speedup of 10x to 20x. But this is still a very specific architecture, and we can wonder if we can do something even simpler and even faster. And this is basically what this work called the transformer network that has been published a few months ago is trying to solve. So beyond trying to make the architecture more simple that we'll describe after, we can also look at the disadvantages of using convolutions or RNNs. For example, if we read a sentence with RNNs or convolutions, we still have issues in learning very long dependencies between very distant input tokens. For RNNs, it requires a linear number of operations, since you have one operation per token in the sequence. And with convolutional networks, if you want to have relations between different words, you need to have convolutional kernels that are longer. So here K is the size of the convolutional kernel. So in both cases, you still have linear in proportion to the sequence. But what a transformer network does is they find relations between input words at any position in a constant number of operations. And they do this by using what they call self-attention or intra-attention, which is basically using the attention mechanism that has been used before, but on the same sequence every time. So here's a basic overview of the transformer network. We can see on the left side, you have the encoder, on the right side, the decoder. And you can see here, there are no convolutions and no RNNs whatsoever. It's only using what they call multi-head attention. So on the encoder side, you use multiple layers of multi-head attention. On the decoder side, you use that same attention on the decoder sequence itself, and then combine the two attentions from the encoder and decoder to compute another attention. And then you use skip connections and feed-forward networks in between to add some nonlinearities. And that's about it. And one more thing to add is just like with the convolutional network, if we don't have any sense of positions, the attention system will not give you any sense of position by itself. So you need to add here again positional embeddings. But unlike the previous work, here the positional embeddings are fixed vectors using sine and cosine functions with different periods, while before we were learning the positional embeddings for each specific positions. The advantage of the fixed ones is that we can scale to arbitrarily long sequences without having to learn sequences that have been arbitrarily long before. So I've mentioned this uses mainly what's called the multi-head attention. It's basically a modified version of the standard dot product attention and using multiple versions of that attention at the same time. So if you recall the dot product attention, you just compute element-wise product between, a dot product between the query and the key, which are Q and K here. And then you do a weighted sum of these scaled weights with the value V. The scaled version is very similar to this, except you add the scaling factor 1 over square root of the hidden dimension of the key. This doesn't change a lot for small hidden sizes, but when you have very large values of K, then you can improve the softmax computation. Once you have this scaled dot product attention, you can basically run multiple versions of this in parallel on the same values, keys, and queries to have attentions that pays attention to different aspects of the sentence itself. So in this paper, they use 8 layers in parallel, or eight heads. Then once you have this concatenation of all the attentions, you can run a feed-forward network on top of that to add some nonlinearities. So they train this model in 2 versions, the transformer. The first one is called the base model. It's trained only for 12 hours on 8 GPUs. And the bid model is trained for 3.5 days. We can see in both cases, they reach either very close to state-of-the-art or state-of-the-art results on WMT for English to German and English to French. And they do this at the fraction of the training cost, either 1 or 2 orders of magnitude less, depending on which model you look and which language pair you look at as well. So it has even more speed up than the convolutional sequence-to-sequence that they compare against as well. So one advantage of using the multi-head attention is it makes the model a bit more interpretable as well. And we can look at the different attentions side by side and see what they pay attention to differently from each other. So here, if you look at the input sequence here, and if you only look at the word making, it has different attentions depending on which head you look at. It's basically trying to see which words are related into making. And you have some attentions looking at more and some looking at difficult at the same time to have a more global representation of the sentence. So this is the overview of that transformer network, and we can do even better with a fraction of the memory overhead. So the idea is that this model still requires many iterations to train efficiently. And if we find a way to make a better use of the multiple attentions, we can do even better, even in terms of blow performance and in terms of compute time. So here, instead of concatenating all the attentions and then running a network on top of them, we're going to learn how important each attention head is. So this is a work that has been done by my coworkers, Karim Hamed and Nitish Keskar. That's called the weighted transformer network. So all it has to do here is, as I said, to just change the attention function. So here, this is the same weighted attention, the same scaled dot product attention that we've seen before. And instead of concatenating these 8 attentions in parallel, we compute a weighted sum of them with 2 weights. We have the Ki weights, which are the concatenation weights that are used here to scale the contribution of each attention before the feed-forward network. And then A, which is the addition weight, with which we compute a weighted sum after we run the feed-forward networks individually for each attention. So this in total adds very few parameters of the transformer, since it's only proportional to a number of attention heads, which in this case is only 8. And the intuition behind this is that it will learn to ease the optimization process to prioritize some attentions compared to other ones. So that in turn reduces co-adaptation and improves generalization later on. So how efficient is this simple modification of the transformer? So here we compare the transformer with the weighted version for many different settings with different number of parameters. So here this is sorted by smaller models into the bigger models. And every time we try to have the same number of parameters. And we can see that in every case, the weighted transformer achieves higher performance while also requiring less training steps to achieve that performance every time. And the speed up to achieve that performance is 15 to 40% faster compared to the base transformer model. So this is a slight modification to keep in mind if you want to use this network for your experiments. So in summary, the transformer and its weighted variant, they push parallelization even further for better clue performance. And it also makes model more interpretable if you look at the different attentions at all the layers of the network. And in future work, this will also be applied to non-textual data like speech data. That's something that could be investigated as well. But the issue with all of the networks we have discussed, including the transformer, is that at inference time, we still need to do the computation sequentially. And this is whether we're using RNNs or attentions or something completely different. The reason for this is when we decode a sentence that we haven't seen before, we have to know which words have been outputted before. And that adds an extra layer of sequence in the decoder. As you can see here, you can generate X, then you have to reuse X before being able to recompute the next word Y. So this is illustrated by this probability equation. If you want to get the probability for a word YT, it always depends on the previous output word Y0 to T minus 1. So you might ask, what if we try to generate all of the words in the output sequence in parallel? Well, there is a naive way of doing this if we just remove this condition of Y0 to T minus 1. And here instead, we only condition the word YT only on the input sequence. And here we have an additional thing to consider is that we need to know in advance the length of the output sequence as well. This is modeled by another probability here, T, which will be the output of the sequence. But if we try this method, we are quickly going to run into issues, mostly because translations are what's called multimodal, which means if you take a given input sequence, you're going to have multiple correct translations that have either sometimes different words and also completely different structures too. And if you try to model each word of these output sequences independently, you're going to run into issues to model what are the right ones and what are the wrong ones. If you take a very simple example from English to German, you can see that thank you can be translated in these two phrases correctly. But then if you only model this word by word, you will also think that danke dank and vielen schön are correct translations. The model will have no way of taking into account which words have been used before or after. So one way to solve this multimodality issue is to introduce what are called latent variables. For example, if we imagine we have a latent variable that will take a different value if we translate into danke schön, and another one if we translate into vielen dank, then we will have a way to distinguish between these two. So what can we choose as a latent variable? There are many ways to approach this issue. We can either create a completely new random variable and then train this based on the data we see. And that's basically the approach that's used on variational autoencoders. But for our use case, there is one variable that we can use as latent, which is called the fertility. So the fertility, this is a concept that has been developed in statistical-based machine translation, especially at IBM. And these are integers for each word in the source sentence that correspond to a number of words in the target sentence that can be aligned to that source word. So if we see in this example, we have the input sentence, we totally accept it. And for here, each we have a fertility predictor. So here, 2 for accept means that in German, we expect the word accept to use 2 German words. And here, it has a fertility of 0. Which means that we think in the German sentence, it will just not be translated at all. One very nice advantage of using the fertility as a latent variable is that implicitly we also know the length of the output sequence once we know the fertilities, which is just the sum of the fertilities. So here we have the modified equation for the probability of an output sequence, which takes into account the probability of the fertility, which is F here, multiplied by the probability of the output tokens. And then we can marginalize this product over the sum of potential fertility sequences here. And the rest of this network is very similar to the transformer. So the way we use fertilities here after we have predicted them is that we copy input words in the output decoder by repeating them as many times as we have the fertility. So here, since we have 1, 1, 2, 0 as a sequence of fertilities, we have we totally accept period as the input of a decoder. So here we have introduced integer variables that are discrete. So we need to have a few modifications to train this model in an efficient way. So first, we can introduce a variational bound to decompose the maximum likelihood loss into basically two losses, which are both negative log likelihoods that can be optimized with algorithms we're used to. So in that case, we can use a translation loss here that's based only on the output tokens, and then the fertility loss that's based on the predicted fertility. And by the way, one way to supervise fertilities and to learn them is to use a hard alignment algorithm trained externally on other data to supervise this model at first. Unfortunately, one thing to realize is that even if we use fertilities, we still have issues with multimodality, which means even if we know in advance the input sequence and the fertilities, we can still have different kinds of outputs in the decoder. The example we've seen before with thank you translated into German still has the same fertilities for both answers. So in order to make the model easier to train and to make the latent variables more relevant, we train on a different data set that is created by knowledge distillation. So we basically used a pre-trained model to generate a new data set where all the inputs and outputs will be coherent, and for the same input, you only have one output. And then we use some policy gradient fine-tuning in the end to train the fertilities independently of the hard alignment algorithm that they have been supervised with, which means that we will sample fertilities and we will try to see if they improve or worsen the performance and then tune them in this way. And we use the reinforced algorithm to do this. So how do we compare? How does this compare against the autoregressive decoder? So unsurprisingly, this does a bit worse since the problem is a bit more challenging, but this gets very close to state of the art on the Romanian to English language pair. As we can see here, NAT is our non-autoregressive transformer. The first one is the basic version. FT is if we had some policy gradient fine-tuning, and NPD is a way to generate sequences that's called noisy parallel decoding, where we sample as many times as we have samples here, either 10 or 100 times. We're using different fertilities, and then we just state the answer that has a highest probability with a given fertility. And then we compare against the transformer version, either with beam search of 1 or 4. So even though it does get better if we use the previous version, we still have a 2% speed up, a 2x speed up if we get close to state of the art from Romanian to English. And if we are okay with having a bit lower performance, we can even achieve 15% speed up in latency. So one interesting thing to look at once we have this network is to see how the output changes if we use different fertilities. So as I mentioned, we have a very close to state-of-the-art model on Romanian to English. So if we take a Romanian sentence as an input, and if we change the fertility for each of the input words, we can have different English sentences as the output, and some of them are very close to each other, and some of them are quite coherent. So the grand truth here is work is being done on solutions like this, but even some before that use different fertilities are still quite good in English. So given all of these words that we have mentioned, there are some future directions that we can take with this. Given that we have been able to make this faster both for training and on inference, we can imagine this model being used to translate even longer documents. Of course, there are more challenges when we're trying to achieve this, such as ensuring global coherence of a document, but what we have just done is a very good step towards that. And we've seen that RNNs and even convolutions are not necessary for most of the MT models if we want to achieve state-of-the-art. So after these developments, I want to look at ways to use more data in the next two parts. This part will be focusing on using different tasks that are being labeled to improve on machine translation. and also how to use machine translation to improve this task in return. So here we're going to deal with the concept of multitask learning, which has been more and more used these days, which is basically using multiple tasks trained on a single model with a single set of weights. The intuition is that in the real world, you may have overlapping structures or tasks that have similar kind of reasoning required to solve them. And maybe mixing two tasks in the same model will help the other task as well. So to do that, you can either define a primary task that will be the one that you're mainly concerned about in terms of accuracy, and an auxiliary task that whose goal is to help the first one. Or in some cases, you can give equal importance to both tasks. And one very related concept of multitask is called transfer learning. So in that setting, we don't train both tasks simultaneously, but we first train one to help on the other separately. And this is a concept that has been used in practice, both in the NLP world and the computer vision world in different ways. For example, in NLP, you may have word vectors like word2vec or globe. And this is basically a prime example of successful transfer learning, where if you used pre-trained word embeddings trained on simple English data, you can improve other subsequent tasks such as machine translation or question answering if we use these word vectors. And in computer vision, this is the same thing that happens when you use the pre-trained convolutional weights that have been trained on ImageNet image recognition. And using most of these convolutional weights on other tasks helps to improve other computer vision models such as feature extraction or object recognition too. So one very specific domain of multitask MT is called multimodal machine translation, which is basically combining MT data with other external contextual data, such as images. So why is this useful? You can imagine yourself as being a tourist in a foreign country, and you know maybe a few words of the foreign language, but you struggle to convey what you mean using only verbal ways. So you may want to point at buildings, to ask for directions, or you may want to mimic something, or just like this person on the picture, you want to point at pictograms or icons to express what you want to convey using nonverbal cues. So this is a similar idea. Maybe using external contextual images will help translation models make better use of this. It turns out there is a dataset that has all these data already at hand, which is called the Flickr multi-30K dataset. One version of this dataset contains images and then descriptions of these images for different languages, such as English and German in this case. So the naive approach will be to use a sequence-to-sequence model and then add the convolutional network that will extract features from the image and test these features as input of the model to maybe improve the German translation. It turns out that in most of the approaches that have been used, simply adding the image does not actually do a lot. But instead, what we can try is to generate the image, or at least generate image features instead of using them as inputs. And this is the principle behind this imagination network. So here I have three main components in this network. We have the shared encoder that reads an English sentence with a bidirectional ASTM. We have a translation decoder, and these two modules together are basically the sequence-to-sequence model that we have seen before. And in addition, if you take the shared encoder, you can also try to predict ImageNet features for the image that is being associated with this input. But you can see here, the image is not taken as the input of the model at all. It's simply tried to be trained on. We try to make the model imagine what an image with such a sentence will look like. What's very impressive about this architecture is that you don't need to have all these three elements at once to train it. You can have maybe one parallel MT dataset that only has sentences, and you can have one image description dataset that only has an English description and an image, which means you can harness even more data than just the Flickr dataset. So the way to train this model is a very standard multitask way of doing this, where you split your loss function into two objective functions. And here you have the weighting factor W to weight the relative importance of one loss function against the other. So here, theta are the shared weights of the model, which are the encoder weights, and phi are the task-specific weights, which are either for the language task or for the representation task. So for the translation loss, this is the basic negative load likelihood loss that we have been using before. But for the image feature loss, we're using a margin-based objective where we're trying to product the ground truth V, and V hat is the features that are generated by the network. So what this loss does is tries to minimize the distance between V hat and V, but we also want to maximize the distance between V hat and a random feature vector that we take from another image, which means that we're trying to be as far as we can from non-relevant examples, but as close as we can from relevant ones. If we only have the first component, we can imagine that most of the vectors will be just as close to each other as possible, and then it will be very hard to distinguish between them. So if we try to compare this model with and without using the image prediction, we can see here this is the base model without images, and this is the model with using images as outputs. And we can see a clear improvement in both Meteor and Blue score. Unfortunately, it doesn't do as best as some phrase-based systems such as Moses, but we can see that the main reason for this is probably that the model we use is fairly simple, and the data set is also not very big compared to other data sets we can train on. But nonetheless, if we look at the image features that are being learned by this model, we can see that it actually does learn very useful things. So here, if you take as an input a native woman is working in a craft project, you can see that the closest neighbors to the image feature that's being computed is actually very relevant to the sentence we have. And similarly, for the second phrase here, there is a cafe on the street corner with an oval painting on the side of the building. We can see that the encoder has a vague sense of what the sentence is trying to convey with buildings and streets and paintings. So in summary, using different kinds of data, such as images, can indeed help machine translation systems when they are used in the right way. Then we can ask ourselves the related question, can we use machine translation to help with other tasks? And if yes, which tasks can be helped? And this is what my colleague Brian McCann has been trying to answer with the work on context vectors. So one very basic way of trying to use MT models for transfer learning will be to first, in A, train a full end-to-end MT model with an encoder and decoder. And B would be to reuse this encoder in the source language and then use the representations that have been learned to train on task-specific models, such as question answering or language inference or classification. So here we have done some experiments on English to German, where we assume that if we train such a model, then you will learn very useful things about the English language that some models may not know about, how to really convey meaning in English, how to disambiguate between words, and how some words play between each other. So in practice, this is how we do. As I said, we train the end-to-end system on A, where the encoder is denoted MTLSTM. And here we take the glove embeddings as inputs of the English language. And then we do the fairly standard attention decoder, and then we generate word-by-word softmaps. But then with B, we throw away completely the decoder and the attention and the softmaps. And all we keep is the MTLSTM that has been unchanged. And then we leave it fixed for the task model subsequent. And we can use the concatenation of the glove vector and the MTLSTM output that we name Cove as the input for the next models. So we can imagine that this can improve for many NLP tasks, but one way to really evaluate how much this improves will be to run all of these tasks into a similar model. So here, this model is not necessary in itself to make use of transfer learning, but this is what we do to evaluate how efficient this really is by just tricking the Cove part of the model. So we run different NLP tasks on this model that has been pre-trained with machine translation. We run sentiment analysis, question classification, natural language entailment, and question answering. So here, the bottom parts of the network, ReLU and encoder, are exactly the MT encoder that we have been trained on. And here, since some of these tasks are using 2 sentences as an input instead of 1, we have to make sentences play between each other to have a global representation. And this is what this Biattention network here is using. Then we concatenate and we pull these representations and then run them through last layer of a maxed out network to have the answer. So to go in a bit more detail about the biattention, if you are not familiar with, there are different ways of doing this, but this is the main idea behind it. We basically want to compute the full attention matrix at once, which is called the affinity matrix in this case, and then compute the normalized weights either across the rows and across the columns as well. And then you can use the content summaries to compute X representation based on Y, and conversely a Y representation based on X. And the intuition is that, for example, if you try to look at a question answering task, you will have a question and a context, and you want to represent the question based on the context, and also represent the context based on the question for better attention. So what happens if we try all of these 4 NLP tasks on this model? And what if we just change the encoder by using some random encoder or just the Cove vector? Well, it turns out that for many of these tasks, and for all of them actually, using the context vectors does help performance. So these are the 3 first ones that are sentiment analysis task on different data sets. The 2 next ones are the question classification. Then we have natural language inference and question answering. So here we compare this same model with using random vectors, glove vectors, character emitting features, or different context vectors that have been trained on data sets with MT of different sizes. As you can see, we have Cove S, M, and L, and each one is about an order of magnitude larger than the previous one. And the reason we use character features as well is that these features are also very complementary to glove and Cove embeddings, because neither glove nor Cove have access to the morphology of words, nor can they disambiguate between unknown words in many cases. You can see here in details, glove plus Cove does improve every time on all the tasks, and glove plus Cove plus character does as well. And if we compare the size of MT data and its influence on transfer learning, we can see that there is a very straight correlation between the size of the MT data set and the performance improvement, which is very conclusive. So far we have only looked at one custom model that we have been trying to fit in all the tasks. But if we compare that model to other state-of-the-art models, we can see that ours does a lot better than all the other ones, especially on SNLI, which is state-of-the-art. And even on Squad, at the time where this paper was published, using Cove obtained state-of-the-art. Today, the numbers of Squad are a bit higher, but even the state-of-the-art models that are not in this table are also using Cove. So in summary, transfer learning from MT task into other NLP tasks is totally doable and very useful. And this is only done by reusing the representations that have been trained with the biased TM encoder. And this work has also inspired others, most specifically ICR submission called the Elmo LSTM. This is a very similar idea, but the idea of that paper is to use language modeling task instead of machine translation task as the basis for transfer. So these are very exciting improvements. But if we see here that we can use some data within MT to use some other task, can we see if we can use data from one MT language to help other ones? In other words, can we do multilingual MT and have some improvements? So we can try to evaluate that and try to see what are the best ways to do multilingual machine translation. So one of the main ways to do this is to use a shared model, or at least shared components of a model, to translate between more than 2 languages pairs. So there are a few approaches that have been tried in the past few years. One main idea is that we can use a separate encoder and a separate decoder for each language. And depending on which parallel dataset we have, we can match some of these encoders together sometimes. But in this approach that has been tried, there is no attention function whatsoever. Another idea is to use the shared attention function for all languages, but to use a separate way of encoding them and decoding them. And the idea is to use the attention to have the global reasoning between words that will be independent of languages. And another way is also to use a shared encoder, but also a separate decoder and attention for each target language. But this only works in the case where you have separate target languages in only one language. But can we do even more simple? Can we do maybe a single shared encoder and decoder for all languages? It's a bit ambitious, but it's fairly easy to try. And this is basically what the Google multilingual model is trying to do. So what they are trying is to take their base architecture, which we have discussed briefly before when we show the tables. It's an 8-layer LSTM encoder decoder. We're using Biattention as well. And what they do is they take that same architecture with the same number of hidden layers and the same parameters, but all they do is to add one extra token in the input sequence. Here you have the English to Spanish pair, hello, how are you, which goes to hola, ¿cómo estás? But all they had is a token that says, please translate this sentence to Spanish, and that's it. And as you can see, there is no token that says what the source sentence is in which language. But the model can actually learn this based on context, and we can learn to disambiguate languages just by looking at them. So one issue that we'll run into if we try to merge all of the vocabularies of all the languages we can try in the same model is that many of the words will be the same. But if we use the word piece vocabulary in that case, then many of the word pieces will be the same between languages, which will help to alleviate the issue of having a super large vocabulary. So as a quick recap, this is the Google NMT architecture. As I mentioned, it has 8 layers using LSTMs and using a bidirectional one, the first encoder layer, and also uses 8 layers in the decoder with skip connections to improve gradient flow. And as you can see, the source sentence is also reversed, which is very common in these kind of models. And the fact it is reversed means that the 2ES token is towards the end of the sentence. So how can we try this multilingual model, and what advantages do we think it's going to have? We can try 3 different types of experiments by increasing order of difficulty. First, we can try to translate many languages into a single one. Second, we can try to translate one languages and try to have many target languages. And then the third type, which is the more ambitious, is to have a single model to translate between many source and many targets. And finally, the authors also try some large-scale experiments with production data that's internal to Google. So if we try the many-to-one approach with different languages such as German to English and French to English, or Japanese to English and Korean to English, we can say in all cases, if we use the same model size, then we have improvements in BLEU score in every case. And this is fairly easy to understand because when you use these joint experiments, you basically double the amount of translation data. So the decoder has more examples in every case in English to know what the English sentence will look like and will be translated in. But on the other hand, if you try to reverse the issue and try to translate from English into 2 separate languages at once, then in some cases you have improvements, but in others you have very big losses, like -2 BLEU scores from English to German. And the issue is because the decoder here has to do twice the amount of work and has to know how to generate 2 completely different languages, which if you use the same number of parameters is a bit more challenging. And finally, if we do the harder problem of translating many languages into many different ones, we can say we still have some losses, but they are relatively small, which is fairly impressive considering we can try to merge 4 models into a single one. And finally, on the production data set that's internal to Google, they do the following experiments. So here they have 12 language pairs, and they use MT data sets that are about 3 orders of magnitude larger than the public ones. Unfortunately, this data is not public, but I wish it was. And here you can see there is a very small difference in the average BLEU score, which is between -5% and -2%. Depending on how many hidden parameters you put in the model. But still, if you consider a single separate model for every pair, you basically have 3 billion parameters in total. But if you combine them into this multilingual model, you have between 255 million and 650 million, which is still a lot less than 3 billion. And one very interesting aspect of this multilingual shared model is you can try to do some experiments on zero-shot translation. So the idea is that if you have one model that's trained from Portuguese to English, and then from English to Spanish. One way to do translation from Portuguese to Spanish, that's actually done in production these days, is just to do one translation and then translate the result again for another network. But that may lose in quality because not all languages can represent all of the aspects of a sentence. For example, English doesn't have genders for many nouns. So if you use Portuguese or Spanish, we do have genders, you're going to lose information a lot. So one way that this model allows us to do is to do explicit bridging. With here, if you look at experiment D with model 1, you train a model on two pairs, Portuguese-English and then English to Spanish. But then if you take a Portuguese sentence and then change the target token by just saying, translate this to Spanish, it does get some decent blue score. Here you have a 21 blue score, which means it still knows a little bit behind how to see how pairs that has never seen before can be translated. With model 2, it's the same idea, but the setting is a many-to-many training, which gives an even higher blue score. Then if you take the model 2 and then add a small amount of parallel data, it actually beats the one that's trained directly from Portuguese to Spanish in C and F. So that's very impressive, and it really makes us wonder what's the level of reasoning that this model is using. If you are not familiar with the concept of interlingua, it's basically the idea that a translation model may be trained to use language-independent representations that can be then reused in any languages. So one way to determine whether the Google model is using interlingua or not is to look at the different representations combined together and see whether they're clustered based on language or clustered based on meaning. And this is the experiment that has been tried in this graph here. Here we have selected English, Japanese, and Korean pairs of different phrases that have the same meaning. Then we're looking at the activations when we translate these word by word or token by token. So in the graph in A, each color has a similar meaning. So we see that indeed phrases with similar meaning are clustered together, which means the model is not really clustering based on language, but really based on meaning, which is evidence for interlingua. And here in B and C, you can see for the same meaning which different languages are present. You can see the Japanese is on the bottom left, the Korean in the middle, and then the English one on the right. So in summary, we just saw that making very simple modifications to the way an MT system treats data can give it powerful multilingual capacities. And we can merge many production systems into a single one with that trick. And we also see some visual evidence for shared representation between several languages, which is very exciting. And if you look at the paper in more detail, and I think one of the authors may present, no, not this one actually, but if you look in the paper in more detail, you'll see more experiments that are also more exciting. You can visualize what zero-shot learning does. You can also try to mix the target language between, like, let's say, Russian and Ukrainian. It actually gives you a mix of Russian and Belarusian, if I remember correctly. So in conclusion, machine translation totally fits with other NLP and non-NLP tasks if you want to improve performance in one or the other. And if you are considering using tasks such as question answering or classification, transfer learning does help a lot as well. And we can also use multilingual for production deployment or for making use of multiple parallel corpora at once for shared target language. And to the grand scheme of things, these are all great ideas and great steps towards more general AI, because if we ever have a general AI in the far future, we want to be able to use many types of data from different sources, even if they don't fit into the simple parallel data. Speaking of which, if we want to go towards more general AI, we can also look into semi-supervised and unsupervised machine translation. So what's the idea behind this? As I said, we can try to use more data that's more widely available, but more importantly, for many languages, we don't really have access to parallel data. For example, if a language is not widely spoken, if it's like a local dialect or an extinct language, or if it's a language that's still widely spoken but not really used online, it's challenging to get data. It can be very costly. So instead, we can try to see if we actually need parallel data to train MT systems, which is a pretty ambitious problem. But first, we can try to look at a simpler problem, which is to learn translations word by word. So here, if we want to use translations word by word, we can start by learning two word embedding matrices, X and Y, that represent source and target languages and different word vectors in them. And then what you can do, which is an idea that has been actually explored by Tomasz Mikolov in the first work-to-vet paper, or in the subsequent papers, is to use a mapping matrix W to rotate the X matrix to get it closer to Y. So this is what the equation 2 is about. You try to minimize the distance between Wx and Y to learn the mapping W. And there are different ways to learn this matrix. You can either approximate with stochastic gradient descent, but it turns out that for this optimization problem, there is an exact solution called the solution to the Procrustes problem. And this is basically using the singular value decomposition between Y and X transposed. And then once you have found the optimal W matrix, you can retrieve translations by using the hard match of the cosine distance between W, X, and Y. The issue with this method that works well in theory is that it only works if you know which rows of X correspond to which rows of Y. In other words, it's a chicken and egg problem. You need to know at least a small amount of parallel words and parallel data in order to optimize this matrix. So this problem, as described here, has to be supervised, or at least semi-supervised. If you have, for example, a small amount of words for which you know translations, you can try to learn W matrix based on that, and then extrapolate translations for other words with the equation number 3. So we can see if there are ways to learn this W matrix in a completely unsupervised fashion, given two independent word embedding matrices. And this is some work that has been done by Kono et al. And submitted to ICLR this year. Here, it works in this way. We start with the setting in the figure A, where we have trained two independent word embedding distributions. One in this example is in English, and the other one is in Italian. So at first, these distributions have nothing to do with each other, and we have no idea which words correspond to each other. First, we can try to get these matrices closer together and learn the rotation matrix W with adversarial learning. So the idea here is that we will sample words either from WX or from Y, and then run them through an adversarial network and try to predict whether a given word came from WX or Y. And if we learn a discriminator to learn the difference, and then if we try to fool the discriminator, we can make WH as close as possible to Y, which means the word will start to correspond a little bit one to each other. And then you can use the previous SVD decomposition in C to actually make these matrices even closer together. As I've said, you need to know a small amount of parallel data to use that solution, but you can assume that the closest words to each other that already exist are the parallel data. And then you can iteratively refine W by taking parallel data and then refining it, etc., etc. And then once the W matrix has converged, you can actually find the nearest neighbors of the word vectors and then figure out that, for example, gatto is translated to cat in that context. So this works very well in theory. In practice, there is one more trick to make sure that we retrieve the correct translations. And the problem is illustrated as follows. When you have these two overlapping word matrices, some words are very close to a lot of other words in the target language, while some others are very distant from all of the other ones. And these are called hubs and anti-hubs. So if you try to find a way to disambiguate between the hubs and the anti-hubs, then you can get better performance in retrieving the translations. So here it works this way. We compute the mean similarity between a given source embedding, WS, compared to its neighboring target vectors, which are represented by the YT in the NT set. And then once you have this mean similarity, which basically means how close a given vector is to its neighbors, then we can compute the cross-domain similarity local scaling distance, which intuitively increases the similarity associated with isolated word vectors and decreases the ones of vectors lying in dense areas. And it's very interesting because it gives us a higher performance without any kind of parameter tuning, so it's great to have. And there is one last challenge to make this solution work, is that since we don't have any parallel data, we also don't have a very precise way of using a def set for cross-validation. So what we do instead, we use an unsupervised model selection criterion, where instead of using the word retrieval from a parallel data, we use the closeness of the source and target embedding spaces metric to determine whether the model will have a good performance or not. So here, if you look at the word translation accuracy, it's very well correlated with the unsupervised criterion that we choose for stopping the model. So we can use this to either choose the best hyperparameters or just to stop the model when training is done. So here are some of the results on word-by-word translation if we use high-quality bilingual dictionaries. So for each of the experiments, we use 1,500 test queries. And for each of the queries, which are single words, we try to find the correct translation word among 200,000 other candidates. And the base embeddings before training are trained with the fast text embedding method. So on the first one, you can see here the methods with the progressive method that I've shown on the first slide, which use supervised learning. And the second one are using completely unsupervised methods. And we can see that for many language pairs, actually using unsupervised methods does better than supervised learning on the same model. And in particular for the English to Italian and Italian to English pairs, even if you use state-of-the-art models that use different approaches, the unsupervised one still does better than state-of-the-art on all of the other ones. So as I've mentioned in the introduction, this can be a very good idea if we want to use low-resource languages. And Esperanto happens to be one of these low-resource languages. It's a language that has very few native speakers. It has somewhat of an online presence, but nearly not as much as English and other languages. So here we can try to do a simple word-by-word translation, and on the left table, you can see the blue score for each direction. So it's clearly not as good as if you had supervised learning, but it still gives some signal. And if you look at the right side of the different translations, you can see that it still conveys the general meaning of the sentence, which is already very important. So except for a few words, like for example, me, which is translated as sorry instead of I, and min, which is translated as hi instead of me, all the other words are giving the right meaning. So putting this aside for a second, we can go over the different ways of using semi-supervised machine translation. So one of the many ways to do this, if we want to use some multilingual data in addition to parallel data to train some MT systems. So there are some very intuitive ways of doing this with existing encoder-decoder networks. And one of the first ways of doing this will be to train a separate language model on multilingual data, and then use that language model with shallow or deep fusion within the encoder-decoder. Shallow fusion will mean that you mix the probabilities of the language model and of the MT decoder to then find mixed probabilities to generate new words. And deep fusion will mean that you use the hidden state of the language model within the encoder itself. But the problem is that using a language model, in many cases, it's the same kind of architecture as the MT model itself. So you have some redundancies in the way you train the system. And the MT decoder is already learning to generate words based on the previous output. So what you can do, instead of having two models, is you can have the same model, but then for the monolingual data, you can generate a dummy source sentence, which will be just using a context vector of 0 in the decoder. But this may lead to some issues if you have too much monolingual data compared to the parallel data. And you can have the issue of catastrophic forgetting. If you have too much monolingual data, then the decoder will only learn to have a language model and not a decoder for MT. So another approach is to generate synthetic source sentences from the monolingual data using batch translation. So here the idea is to translate two MT models for each direction, and then to refine one of them by using synthetic data created by the other one. So this idea works only if you have semi-supervised data when you are able to translate at least some amount of data from an existing system. But then you can also try to do it completely unsupervised with the following method, which is some work that has been also submitted at ICLR this year. So here, what we're trying to do with completely unsupervised data with no correspondences between source and targets, we're trying to map them into a shared latent space, which is denoted by Z here. So you first take a noisy version of a sentence, here it's CH, encode the latent space using the standard encoder that we've seen, and then decode with X hat, and then try to make X hat as close as possible to X. And then if you use batch translation to generate a translation Y, you can also generate another translation from a noisy version of Y, then back into latent space, and then back into the target domain with X. So this is very interesting, but you might ask, how do we do the batch translation? What do we start with? Then remember that we have the word-by-word unsupervised model that we have trained just before. So if you initialize that batch translation with the word-by-word model, you can still have a totally unsupervised method that will still try to match source and target sentences in the same space and hopefully do translation efficiently. So the way this is done, it has different loss functions. We first trained the denoising autoencoder that was on the left side of the chart, and then train the translation with the batch translated source sentence, so which are L-auto and L-city on this chart. And then just like for the unsupervised word translation, you want to make sure that both languages are mapped into a shared latent space with same distributions. And here again, we use adversarial learning to fool the discriminator to think that one representation comes from one language or the other. And as I mentioned, we can use the unsupervised word-by-word translator as the first epoch of that iterations. And just like before, we need a way to select the best model without having parallel data. So here, the way to do this is to translate one sentence from language 1 to language 2, back to language 1 with the model we're trying to evaluate. And then we compute the blue score between the original sentence and the reconstruction. And then we average the blue score over all the sentences in both directions of language in the dataset. As we can see, the green, which is our criterion, is fairly well correlated with supervised blue scores. And here are some results compared both with the supervised learning approach and with some unsupervised baselines, including the word-by-word translation. You can see that in both cases, our model still does worse for the same amount of data, but still has a fairly well manifested signal, within 32 for English to French, for example. But as I mentioned, this will be useful not really for high resource languages, but for low resource ones. So if we try to compare the unsupervised performance, which is the horizontal bar here, against MT systems trained on less data, then the unsupervised version is actually better than MT systems trained with about less than 100,000 sentence pairs, which is still very significant. For many language pairs, we don't have as many sentence pairs as this. So this is definitely a baseline that can be used for developing systems for new languages. And here are some examples of translations using that completely unsupervised fashion. So here from French to English, you can see that at iteration 3, which is the last one of the unsupervised system, the sentences get fairly close, except for a few words that still convey the same meaning. It's basically a refinement of the word-by-word translation we have seen before. So to summarize, this is a very good proof of concept that I really hope will warrant further research in the future. And this will be very useful if we want to make systems for many more languages. And we might ask ourselves, is this method really useful to make production-ready models on virtually any language? I think that's a hope that will be achievable in the near future if we do more and more research on these semi-supervised and completely unsupervised languages and MT. So in general conclusion, we have seen ways to speed up machine translation systems and start from RNNs and to gradually replace them with convolutions or just completely attentions. We have used multitask, multilingual data, and we can see further improvements in performance with them. And also some first steps of nice proof of concepts with non-autoregressive decoding of generating every word at once or completely fully unsupervised translation. So I haven't had time to take on many of the challenges of MT, of course. There are still a lot of research problems that we can work on these days. Can find better evaluation metrics, which I think is something that some of the speakers this week will talk about. We still find better ways to use more context, more than just one image. Then we can find better representations for modeling different translation modes if we want to know how to translate the same sentence in different ways. So if you want to work on more cool problems like this, we are hiring. If you want to come work in Palo Alto, California, just send me an email or go in the address. Thank you.
Okay. Thank you for the talk, and now we can we have some time for questions. Guys, does anyone have any questions? Yes, please.
Thank you very much for your talk. So my question is, when we're looking at the paper and actually the code for word translation without parallel data, they were using normalized word vectors. So they make sure that every word vector is on the sphere, unit sphere, and it makes probably the translation easier. So you just have to rotate the sphere to match the vectors. But on the other hand, it seems there is an evidence that non-normalized word vectors perform better for many tasks. Like we had an experiment with Stanford NLI dataset, and when we normalize the vectors, the performance gets lower. Can you share your experience with this? So is this a normalization, like can we avoid this normalization for word translation in an unsupervised way, or we can actually train better models for supervised tasks with normalized vectors?
Thanks for the question. So it's a very good question. I actually haven't used this particular method in production, so I have very little experience in how normalizing or not affects the performance. But we can try to use that method without normalization and see how well it performs. But otherwise, yeah, it warrants further experiments, and I don't really have a clear answer for that.
And one more question about your work on non-autoregressive models. So I think, as far as I could understand, the speed up that you mentioned was like 2 or 3 times, which seems to be quite low, right? You can expect speed up at least as many times as you have words in the sentence. What was the reason for that, or it was something different?
So if you look at the different experiments, we actually have different speedups depending on the different settings of the model. And the reason why the speedup is not as fast in some cases is because of the noisy parallel decoding in the last 2 experiments. And what this does is basically samples more than one output every time and then pick the best one to find as the global output, which means you're actually doing 100 outputs in parallel instead of using a single one. But if you do a single output, then the first 2 ones are actually a 15x speedup. So it's a trade-off between how much of a performance increase you want to have. Yeah.
Okay, thank you. Any more questions? Okay. Are you going to ask a question?
Hi. I have a question about Cove. You have no comparison with InferCent in your paper, but as I understood, it's also the embedding of the whole sentence, yes?
Which model are you talking about?
It's Cove. It's
yeah, I mean, compared with what? Which one?
I mean, in context vectors, do you use them to embed the whole sentence? And
yes.
And have you compared them to the InferCent in terms of quality of embedding? So, for example, for SNLE or something like this.
All right. So if you look at their experiments here, we compare them against Cove, and they gave random vectors, and against Cove, depending on the size of the MT data. So that's all we try here.
So as I understood in percent, it's just came out later than you have submitted the paper. But after that, have you tried to compare them or not?
No, we haven't.
Okay, and I also have a question about these contextual vector embeddings. Because in the first part of your talk, you told a lot about the convolutional encoding. But here you are using recurrent networks to encode the sentence. So have you tried to use convolutional layers here, or?
That's a very good question. So we haven't, but one reason we haven't is because in the convolutional network, this is also based on many layers of attention to be performant. But here we try to have a single component, which is the encoder, to have global representations. I'm not sure that the representations based on the convolutional layers without any attention will be as efficient, but that could be tried in the future.
Okay, thank you. And the final question is about what do you think that we know that a lot of models from machine translations there are a lot of attempts to use them for the dialogue systems. And what do you think? What is if you judging from the current state of machine translation models, like because all of them sequence to sequence models, what is the best approach? What models should be used for the dialogues? What we should try? What should be the difference? Can you get your opinion on that?
So I think many of the components that we have described can be reused, but the extra difficulty with dialogue is that the outputs and inputs are way longer, and you have to keep track of the state in a better fashion. So I think in many cases, adding a state tracking capacity to these networks will solve many of the issues. But that goes back to the problem that I have described, which is even if we have faster models, we still need to ensure global coherence. So then you have to distinguish between open domain dialogue and task-specific dialogue as well. If you want to train on task-specific dialogue, then it's a bit easier to model the state and what kind of task you want to have. With open dialogue, it still really depends of what you're trying to achieve with such models.
Okay, thank you.
Okay, maybe one last question. Okay, then let's just thank our speaker again.